Einstein told us nothing can move faster than light, 299,792,458 meters per second. That's the number that defines the structure of reality itself. For over a century, this cosmic speed limit has stood as the ultimate barrier in our universe. Every spacecraft we've ever built, every particle we've accelerated, every signal we've transmitted has been bound by this fundamental law. But what if there's a loophole? What if the very fabric of space and time holds secrets that could let us sidestep this seemingly unbreakable rule? Could we one day travel across the galaxy in a human lifetime without tearing physics apart? The implications are staggering. If we could somehow exceed the speed of light, the nearest star system, Alpha Centauri, would be reachable in years instead of millennia. The Milky Way galaxy, stretching 100,000 light-years across, could become our playground rather than an impossible frontier. Civilizations separated by cosmic distances could finally meet face to face. Yet every time scientists have tried to break this barrier, nature has pushed back. Particle accelerators consuming the power of entire cities can't push even the smallest particles past light speed. The faster something goes, the more energy it needs, until reaching light speed would require infinite energy. It's as if the universe has built an impenetrable wall at exactly 299,792,458 meters per second. But here's the thing about walls. Sometimes you don't have to break through them. Sometimes you can find a way around them. And in the deepest equations of physics, there might just be pathways that lead beyond the speed of light without ever crossing that forbidden threshold. To find these loopholes, we have to understand why light speed is a limit in the first place. The answer will take us on a journey through the strangest corners of physics, where space can bend, time can stretch, and the impossible might just become inevitable. In 1905, a young patent clerk named Albert Einstein published a paper that would forever change our understanding of reality. He called it special relativity, and buried within its elegant equations was a shocking revelation. The speed of light in a vacuum, exactly 299,792,458 meters per second, isn't just the speed that light travels, it's the absolute speed limit of the universe itself. But why? What makes this particular number so special? The answer lies in the very fabric of space and time, and it's far stranger than most people realize. Imagine you're driving down a highway at 60 miles per hour. To you, sitting in the driver's seat, you're perfectly still. The world outside rushes past your windows. But to someone standing on the roadside, you're moving at 60 miles per hour. This seems obvious, right? Speed is relative. It depends on your perspective. Now here's where things get weird. Imagine instead of driving a car, you're somehow riding on a beam of light, traveling at 299,792,458 meters per second. According to everything we know about everyday physics, someone standing still should see you zooming past at light speed. But someone chasing you in another light beam should see you as stationary, just like two cars traveling at the same speed on a highway. Einstein realized this creates an impossible contradiction. Light doesn't behave like cars on a highway. No matter who's observing it, no matter how fast they're moving, light always travels at exactly the same speed. 299,792,458 meters per second. Always, without exception. Think about how radical this is. If you're standing still and I shine a flashlight, you measure the light traveling away at light speed. If you hop in a rocket ship and chase that light beam at 90% of light speed, you still measure it moving away from you at full light speed, not 10% of light speed, which is what common sense would suggest. The full, unchanged speed of light. This isn't just theory. We've tested it millions of times in laboratories around the world. Every single measurement confirms Einstein's bizarre prediction. Light speed is constant for all observers, no matter how they're moving. But if light speed is constant, something else has to give. And that something is space and time themselves. When you try to catch up to a light beam, space contracts around you and time slows down. These aren't just mathematical tricks or optical illusions. They're real, measurable changes to the fundamental structure of reality. As you approach light speed, a meter stick becomes shorter than a meter. A second becomes longer than a second. Your mass increases toward infinity. Let's follow this logic to its terrifying conclusion. Imagine you're in a spacecraft accelerating toward light speed. At first, everything seems normal. You're traveling at 10% of light speed, then 20%, then 50%. Your rocket engines are working perfectly, pumping energy into your acceleration. But as you approach light speed, something strange happens. The same amount of energy that used to increase your speed dramatically now barely budges your velocity. You're at 90% of light speed, then 95%, then 99%. Each incremental increase requires exponentially more energy. At 99.9% of light speed, you need enormous amounts of energy for tiny gains. At 99.99%, the energy requirements become astronomical. By the time you reach 99.9999% of light speed, you'd need more energy than exists in the entire observable universe just to gain another fraction of a percent. And here's the killer. To actually reach 100% of light speed, to actually touch that magic number of 299,792,458 meters per second, you'd need infinite energy. Not just a lot of energy, not just more energy than we can currently produce, infinite energy, which is impossible. This is why massive objects can never reach light speed. The universe simply won't let them. It's not a technological limitation we might overcome with better engines or more advanced materials. It's built into the fundamental structure of reality itself. But wait, there's more. As you approach light speed, time itself begins to break down around you. From your perspective inside the spacecraft, everything seems normal. Your clocks tick normally. Your heartbeat feels regular. Your thoughts move at their usual pace. But to anyone watching from outside, your time has slowed to a crawl. At 90% of light speed, your time moves at about 43% of normal speed. A year for you equals 2 1/3 years for everyone else. At 99% of light speed, your time crawls at just 14% of normal. A year for you becomes 7 years for the outside world. By the time you reach 99.999% of light speed, time dilation becomes extreme. A single day in your reference frame could equal years or even centuries in the outside world. And if you somehow manage to reach exactly light speed, which remember is impossible for massive objects, time would stop completely from an outside perspective. This isn't science fiction. This is experimentally verified science. Particle accelerators routinely push subatomic particles to over 99% of light speed, and we observe exactly these effects. The particles live longer than they should because their internal clocks are running slow. They require enormous energies to gain tiny increases in speed. Every prediction of special relativity plays out exactly as Einstein calculated over a century ago. The most powerful particle accelerator on Earth, the Large Hadron Collider in Europe, can accelerate protons to 99.999991% of light speed. That's just 9 parts in a trillion away from the speed of light. But even with 27 kilometers of superconducting magnets consuming the power of a small city, it still can't push those protons any closer to the ultimate speed limit. Here's what makes this even more remarkable. Photons, the particles of light itself, have no mass, zero mass. And because they have no mass, they don't experience the infinite energy problem that stops massive objects. They can travel at exactly light speed. In fact, they must travel at exactly light speed They can't go any slower, and they certainly can't go any faster. This creates a fundamental divide in the universe. Massive objects, everything from electrons to planets to galaxies, can approach light speed but never reach it. Massless particles like photons must travel at exactly light speed, no faster, no slower. It's as if nature has created two separate categories of existence, divided by this one magical number. But photons pay a price for their speed. Because they travel at light speed, they experience no time. From a photon's perspective, if photons could have perspectives, the moment it's created and the moment it's absorbed happen simultaneously. A photon that travels for 13 billion years across the universe experiences zero time during that journey. This is the reality we live in, a universe where space and time are not separate things, but part of a unified fabric called space-time, where speed, time, energy, and mass are all interconnected in ways that defy our everyday experience, where the faster you go, the more energy you need, the slower your time moves, and the more massive you become. It's a universe with an absolute, unbreakable speed limit built into its very foundation. 299,792,458 meters per second. Not just the speed of light, but the speed of causality itself. The speed at which cause and effect can propagate through space-time. The mathematical elegance of this speed limit is breathtaking. In Einstein's famous equation, E equals mc squared, that c represents the speed of light. But it's more than just a conversion factor between mass and energy. It's the fundamental constant that defines the relationship between space and time. Change the speed of light, and you change the entire structure of reality. Scientists have spent over a century testing this speed limit, and it has never failed. In 1971, physicists Hafele and Keating flew atomic clocks around the world on commercial airliners. When they compared these traveling clocks to stationary ones, they found exactly the time differences Einstein predicted. The flying clocks had gained time because they were moving faster relative to the Earth's surface. GPS satellites provide an even more dramatic example. These satellites orbit Earth at about 14,000 kilometers per hour. At that speed, special relativity predicts their clocks should run slow by about 7 microseconds per day compared to clocks on Earth's surface. That might not sound like much, but GPS requires nanosecond precision to calculate your position accurately. Without correcting for relativistic effects, GPS would become useless within hours. But the speed limit isn't just about clocks and satellites. It fundamentally limits how fast information can travel through the universe. When you flip a light switch, the electrical signal travels down the wire at close to light speed, but never faster. When you send a text message, the electromagnetic waves carrying your message propagate at light speed through the air and through fiber optic cables. When stars explode in distant galaxies, we see the light from those explosions only after it has traveled for millions or billions of years at light speed. This creates what physicists call the light cone, a fundamental structure in space-time that determines what events can influence what other events. Imagine standing in a field and dropping a stone into a still pond. Ripples spread outward from the impact point at a specific speed. Events outside those ripples can't be affected by your stone until the ripples reach them. The universe works the same way, except the ripples are traveling at light speed. Any event, whether it's a star exploding, a signal being sent, or a particle collision, creates an expanding sphere of influence moving outward at light speed. Events outside this sphere cannot be causally connected to the original event until light has had time to travel between them. This isn't just a limitation on communication or transportation. It's a fundamental aspect of causality itself. Without the light speed limit, cause and effect could become scrambled. Events could influence their own past, creating paradoxes that would tear apart the logical structure of reality. Consider what would happen if you could send a message faster than light. You could send information to a distant star instantly. Someone on that star could immediately send a reply. But because of the way different reference frames work in relativity, under the right conditions, that reply could arrive before you sent your original message. You'd receive an answer to a question you hadn't asked yet. You could potentially prevent yourself from sending the original message, creating a grandfather paradox in spacetime. The speed of light isn't just a speed limit, it's a causality limit. It's what keeps the universe logically consistent and prevents paradoxes from destroying the fabric of spacetime itself. Yet despite this seemingly unbreakable barrier, the universe holds deeper mysteries. Einstein's special relativity, published in 1905, deals with objects moving through space. But 10 years later, in 1915, he published general relativity, which revealed that space and time themselves could be curved, stretched, and manipulated by mass and energy. And here's where things get interesting. While special relativity forbids anything from moving through space faster than light, general relativity places no such restriction on space itself. Space can expand, contract, ripple, and wave at any speed whatsoever. During the first fraction of a second after the Big Bang, space itself expanded faster than light, carrying distant regions of the universe away from each other at superluminal speeds. Even today, galaxies at the edge of the observable universe are receding from us faster than light because the space between us and them is expanding. We can't see beyond a certain distance, not because light hasn't had time to travel that far, but because space is expanding so quickly that light from those regions is being stretched and redshifted into oblivion. This distinction between motion through space and the motion of space itself opens up possibilities that would have seemed impossible under special relativity alone. If we can't move through space faster than light, perhaps we can find ways to manipulate space itself, to surf on waves in space-time rather than trying to swim against its current. The speed limit remains absolute for motion through space. 299,792,458 meters per second. No exceptions. But the door is open for something far more exotic. Something that could let us traverse the cosmos without ever breaking Einstein's fundamental law. Or so it seems, because while Einstein's special relativity sets this speed limit for motion through space, it says nothing about what might happen if space itself could be manipulated, twisted, or folded. And that's where our story really begins. Here's the thing about Einstein's speed limit that almost everyone gets wrong. When physicists say nothing can travel faster than light, they're not talking about what you think they're talking about. The rule is incredibly specific, and understanding exactly what it does and doesn't forbid is the key to unlocking the universe's greatest loopholes. Special relativity forbids local motion through space faster than the speed of light. Let me repeat that with emphasis on every crucial word. Local motion through space, not motion in general, not all types of faster than light phenomena, just local motion through space. What does local mean? It means within a small region of space-time where the effects of gravity and space-time curvature can be ignored. What does motion through space mean? It means an object changing its position relative to the coordinate system of space-time around it. This is the kind of motion you experience every day. Walking across a room, driving down a highway, or launching a rocket to the moon. In every case, you're moving through the existing structure of space. But here's the crucial distinction that opens up entirely new possibilities. Einstein's theory says absolutely nothing about space itself moving, expanding, contracting, or being manipulated in ways that could carry objects along with it. Think about it this way. Imagine you're standing on a moving walkway at an airport. The walkway is moving at 3 miles per hour, and you're walking on top of it at 3 miles per hour in the same direction. To someone standing beside the walkway, you appear to be moving at 6 miles per hour. But you haven't broken any speed limit for walking. You're still walking at exactly 3 miles per hour relative to the surface beneath your feet. The walkway itself is doing the extra work of carrying you forward. Now imagine that instead of a walkway, you're standing on a section of space that's moving, expanding, or contracting. If space itself carries you faster than light, you haven't broken the speed limit for motion through space. You're still stationary relative to your local patch of space-time. Space itself is doing the work of moving you faster than light relative to distant observers. This isn't just theoretical speculation. The universe provides us with a perfect example that's happening right now, all around us, on the largest scales imaginable. The universe is expanding, not just growing larger, but actually expanding, with space itself stretching like a balloon being inflated. This expansion was first discovered by Edwin Hubble in 1929, when he noticed that distant galaxies were moving away from us. The farther away a galaxy was, the faster it appeared to be receding. At first, astronomers thought this meant the galaxies were flying through space away from us, like debris from some cosmic explosion. But as they studied the phenomenon more carefully, they realized something far stranger was happening. The galaxies weren't moving through space. Space itself was expanding, carrying the galaxies along with it. Here's where it gets really interesting. Because space itself is expanding, there's no limit to how fast this expansion can occur. Galaxies can recede from us faster than the speed of light, and they regularly do. Consider a galaxy located 15 billion light years away from us. The expansion of space is carrying this galaxy away from us at about 1.5 times the speed of light. That's 449,688,687 meters per second, 50% faster than the cosmic speed limit. But the galaxy isn't breaking any rules. It's not moving through its local space at faster than light speed. From the perspective of anyone living on that galaxy, they're sitting perfectly still in their local region of space-time. It's the space between us and them that's expanding, creating the separation at faster than light speeds. This happens because the expansion rate of space is proportional to distance. The Hubble constant, which measures how fast space expands, is about 70 kilometers per second per megaparsec. That means for every megaparsec of distance, which is about 3.25 million light years, space expands at an additional 70 kilometers per second. Do the math, and you'll find that at a distance of about 14 billion light years, the expansion velocity equals the speed of light. Beyond that distance, galaxies recede faster than light. Much farther out, at distances of 30 or 40 billion light years, galaxies are racing away from us at 2 or 3 times the speed of light. These galaxies exist in what cosmologists call the zone of avoidance. We can never communicate with them, never visit them, never even see them as they are now, because light from them can never catch up with the expansion of space to reach us. They're forever beyond our cosmic horizon. But here's the remarkable thing. This faster-than-light recession isn't just happening in the distant universe. It happened to us. During the first tiny fraction of a second after the Big Bang, the universe underwent a period called cosmic inflation. Space expanded exponentially, stretching regions that were once close together to enormous distances in an incredibly short time. During inflation, space expanded much faster than the speed of light. Points that were separated by microscopic distances at the beginning of inflation ended up separated by distances larger than our current observable universe, all in less than a trillionth of a trillionth of a trillionth of a second. This superluminal expansion is why the cosmic microwave background radiation, the afterglow of the Big Bang, looks so uniform in all directions. Regions of space that appear to have never been in contact with each other actually were in close communication before inflation separated them faster than light could travel between them. Alan Guth, who first proposed cosmic inflation in 1980, called it the ultimate free lunch. The universe got something for nothing by expanding space itself rather than trying to accelerate matter through space. No energy was required to exceed the speed of light because nothing actually moved through space faster than light. This expansion of space reveals the first and most important loophole in Einstein's speed limit. The rule forbids local motion through space faster than light. It says nothing about space itself moving, expanding, or being manipulated in other ways. But cosmic expansion is just the beginning. Einstein's general theory of relativity, published in 1915, revealed that space and time are not fixed background stages on which physics plays out. They're dynamic, flexible, responsive to matter and energy. Mass and energy curve spacetime, and curved spacetime tells matter how to move. This means spacetime is malleable. It can be stretched, compressed, twisted, and deformed by the right kinds of matter and energy. And if spacetime can be manipulated, then perhaps we can find ways to manipulate it that allow faster than light travel without anyone or anything ever moving through space faster than light. The mathematics of general relativity are incredibly rich and complex, filled with exotic solutions that seem to come straight out of science fiction. Wormholes that connect distant regions of spacetime, closed time-like curves that loop back on themselves, regions where space and time swap roles, and yes, configurations of matter and energy that could theoretically propel a spacecraft faster than light by manipulating the spacetime around it. These aren't violations of relativity. They're solutions to Einstein's equations, allowed by the very theory that sets the speed limit in the first place. They respect the fundamental rule that nothing moves through local space faster than light, while potentially allowing faster than light travel through spacetime manipulation. But there's always a catch. Just because something is allowed by the equations doesn't mean it's possible to build in reality. Many of these exotic solutions require forms of matter and energy that may not exist, or that would require technology far beyond anything we can currently imagine. The question isn't whether general relativity allows faster than light travel through spacetime manipulation. It does. The question is whether the universe provides us with the tools to actually build these spacetime manipulating devices, or whether they remain forever trapped in the realm of mathematical possibility. This is where the story gets really interesting, because while we can't yet manipulate spacetime in the extreme ways required for faster than light travel, we're beginning to understand how such manipulation might work. We're starting to glimpse the engineering challenges involved, and we're discovering that the universe itself provides examples of exactly the kinds of space-time manipulation we'd need to achieve. The speed limit remains absolute for local motion through space: 299,792,458 meters per second. But space itself follows no such restriction. It can expand, contract, twist, and deform at any rate whatsoever. And if we can learn to surf those waves in space-time rather than swimming against them, the entire galaxy could become accessible within a human lifetime. The rule doesn't say what most people think it says. It forbids moving through space faster than light. It says nothing about moving space itself, or about riding waves in space-time that carry us faster than light, without ever requiring us to exceed the speed limit locally. Understanding this distinction is the first step toward grasping how we might one day slip through the cosmic speed limit without ever breaking it. The universe has already shown us it's possible. Now we just need to figure out how to do it ourselves. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was watching an episode of Star Trek. Like millions of other viewers, he was fascinated by the Enterprise's warp drive, which allowed the starship to travel faster than light by warping space around it. But unlike most viewers, Alcubierre had the mathematical tools to ask a crucial question: could such a thing actually work? What he discovered changed everything we thought we knew about faster than light travel. Not only could a warp drive work in principle, but Alcubierre found a way to describe it using Einstein's own equations. He had discovered the first scientifically rigorous method for exceeding the speed of light without breaking any laws of physics. The Alcubierre drive doesn't move a spacecraft through space faster than light. Instead, it moves space itself, creating a wave in spacetime that carries the ship along like a surfer riding a wave. The ship never exceeds the speed of light relative to the space immediately around it. But the wave in spacetime can travel as fast as you want, potentially crossing galactic distances in days or weeks. Here's how it works. Imagine space as a flowing river. Normally, if you want to travel upstream faster than the current, you need to swim harder and harder as you go faster. Eventually, you reach a maximum speed determined by how hard you can swim. This is like trying to accelerate through normal space, where you hit the light speed barrier as your energy requirements become infinite. But now imagine you have the power to manipulate the river itself. Instead of swimming upstream, you create a wave that carries you forward. You're not moving relative to the water immediately around you. You're sitting still in your little pocket of water while the wave does all the work of propelling you forward. The wave can move as fast as you want because you're not the one providing the energy to move through the water. The Alcubierre drive works on exactly this principle, but with spacetime instead of water. It creates a region around the spacecraft where space contracts in front and expands behind. The ship sits in a flat region of spacetime between these two zones, never moving relative to its local space, while the wave in spacetime carries it forward at whatever speed you design into the system. The mathematics are surprisingly elegant. Alcubierre starts with Einstein's field equations, the fundamental equations of general relativity that describe how matter and energy curve spacetime. He then asks what kind of matter and energy distribution would be required to create the specific pattern of spacetime curvature needed for a warp bubble. The answer involves something called the expansion scalar, which measures how much spacetime is stretching or contracting at any given point. In front of the warp bubble, you need spacetime to contract, bringing distant points closer together. Behind the bubble, you need spacetime to expand, pushing points farther apart. The ship rides in the flat region between these zones of contraction and expansion. Think of it like an escalator made of space itself. The steps in front of you are getting closer together, effectively shortening the distance you need to travel. The steps behind you are spreading apart, increasing the distance you've already covered. You're not moving relative to the step you're standing on, but the escalator carries you forward at whatever speed the steps are moving. The beauty of this system is that there's no theoretical limit to how fast the warp bubble can travel. Want to cross the galaxy in a year? Design the bubble to move at 100,000 times the speed of light. Want to visit nearby star systems in a matter of days? Crank up the warp factor even higher. The ship inside never experiences acceleration, never approaches the speed of light locally, and never violates any speed limits. From the perspective of someone inside the warp bubble, the journey is remarkably peaceful. There's no acceleration, no G-forces, no time dilation. You could travel from Earth to the Andromeda Galaxy, a distance of 2.5 million light-years in a matter of weeks or months, and you'd experience every minute of that journey normally. No relativistic effects, no time passing differently for you than for people back on Earth. But here's where the dream starts running into harsh reality. The matter and energy required to create an Alcubierre warp bubble are unlike anything we've ever encountered in nature. To contract space in front of the bubble and expand it behind, you need something with negative energy density. Not just a small amount of negative energy, but vast quantities of it, arranged in precisely the right configuration. What is negative energy? It's exactly what it sounds like: matter or energy that has less than zero energy content. In our everyday experience, energy is always positive. A moving car has kinetic energy. A stretched rubber band has potential energy. A hot cup of coffee has thermal energy. All of these energies are positive numbers. But quantum mechanics reveals that empty space isn't really empty. It's filled with quantum fluctuations, virtual particles that pop into existence and disappear again on timescales so short that they don't violate conservation of energy. These fluctuations create what physicists call vacuum energy or zero-point energy. In certain circumstances, you can manipulate these quantum fluctuations to create regions with less energy than empty space. This is negative energy density, and it's been observed in laboratory experiments like the Casimir effect. Place two metal plates very close together in a vacuum, and the quantum fluctuations between the plates become restricted. There are fewer possible quantum states between the plates than in the vacuum outside, creating a region of negative energy density that pushes the plates together. So negative energy exists. The problem is scale. The Casimir effect produces tiny amounts of negative energy, barely enough to lift a grain of sand. To power an Alcubierre drive capable of faster-than-light travel, you'd need negative energy equivalent to the mass energy of entire planets or stars, all concentrated in a thin shell around your spacecraft. Let's put this in perspective. Einstein's famous equation E equals mc squared tells us that mass and energy are interchangeable. The mass of our Sun, about 2 × 10⁻30 kilograms, corresponds to an energy of about 2 × 10⁻47 joules. To create a warp bubble around a spacecraft the size of the Enterprise, Alcubierre's original calculations suggested you'd need negative energy equivalent to the mass energy of Jupiter, which is about 1 × 10⁻45 joules. That's the energy output of our Sun for over 300 million years. Except it needs to be negative energy, and it needs to be precisely arranged in a thin shell around your spacecraft. We're not talking about advanced engineering here. We're talking about manipulating more energy than human civilization has used in its entire history, and doing it with a form of energy that we can barely produce in microscopic quantities. But the story doesn't end there. In the years since Alcubierre's original paper, physicists have found ways to dramatically reduce the energy requirements. Chris van den Broek showed that by changing the geometry of the warp bubble, making it very small inside and tapering smoothly to flat space outside, you could reduce the energy requirements by many orders of magnitude. Instead of needing the mass energy of Jupiter, Van den Broek's improved design might work with negative energy equivalent to just a few tons of matter. That's still an enormous challenge, requiring us to produce and control millions of times more negative energy than we can currently create. But it's no longer completely beyond the realm of possibility. More recent work by physicists like Harold White at NASA has explored even more exotic possibilities. What if you could oscillate the warp field, turning it on and off rapidly? What if you could use higher dimensional effects predicted by string theory? What if you could find natural sources of negative energy in the universe? These are all highly speculative ideas, but they point toward a future where warp drive technology might be achievable with advanced but not impossible engineering. We're not talking about technology we could build tomorrow or even in the next century, but we might be talking about technology that an advanced civilization could develop given enough time and resources. There are other challenges beyond just the energy requirements. The warp bubble would need to be incredibly stable. Any fluctuations in the field could tear the spacecraft apart or strand it in deep space. The bubble would need to be controllable, able to accelerate, decelerate, and change direction. And somehow, the crew inside would need to be able to communicate with the outside universe to navigate. Some physicists have also raised concerns about causality. If you can travel faster than light using an Alcubierre drive, could you potentially travel backward in time and create paradoxes? The mathematics suggest this might be possible under certain conditions, which could make warp drives fundamentally incompatible with the logical structure of space-time. But despite all these challenges, the Alcubierre drive remains one of the most promising theoretical approaches to faster-than-light travel. It respects Einstein's speed limit by never requiring anything to move through space faster than light. It uses only general relativity, without requiring speculative physics beyond our current understanding. And while the engineering challenges are enormous, they might not be impossible forever. NASA has even conducted preliminary experiments to detect space-time distortions that might be signatures of Alcubierre drive effects. Their interferometer experiments haven't detected anything yet, but they've established that such signatures could theoretically be measured with sufficiently sensitive equipment. The Alcubierre drive shows us that faster-than-light travel isn't forbidden by physics. It's just incredibly difficult to engineer. The universe allows it in principle, but demands a price in exotic matter and energy that we can't currently pay. But here's the thing about impossible engineering challenges. History is full of them becoming possible. Powered flight was impossible until 1903. Rockets to the moon were impossible until 1969. Computers that fit in your pocket were impossible until the 21st century. The question isn't whether we can build an Alcubierre drive today. We obviously can't. The question is whether we can build one someday, and whether the fundamental physics of the universe permit such devices to exist. The answer, according to our best current understanding of general relativity and quantum mechanics, is a cautious yes. The universe allows warp drives. Whether we'll ever develop the technology to build them is another question entirely. But for the first time in human history, we have a scientifically rigorous blueprint for exceeding the cosmic speed limit. Space can be warped, twisted, and manipulated by the right kinds of matter and energy. Ride those waves in space-time, and the galaxy becomes accessible without ever breaking Einstein's fundamental rule. The Alcubierre drive isn't science fiction anymore. It's science fact, waiting for engineering to catch up with theory. In 1935, Albert Einstein was working on what would become his final major contribution to physics. Along with his colleague Nathan Rosen, he was exploring the mathematical implications of his general theory of relativity when they stumbled upon something extraordinary. Hidden within Einstein's equations was a solution that described a bridge through space-time itself, connecting two distant regions of the universe through a tunnel that could theoretically be traversed faster than light, could travel between the same 2 points through normal space. They called it an Einstein-Rosen bridge, though the scientific world would later know it by a more evocative name: wormholes. Shortcuts through the fabric of space-time that could make the impossible journey across cosmic distances not just possible, but routine. The concept of a wormhole is both elegant and mind-bending. Imagine space-time as a flat sheet of paper. In normal space, traveling from one point to another means moving across the surface of the paper. The shortest path is a straight line, and that path has a definite length. Light traveling between 2 points must follow that path, setting the minimum travel time between those locations. But what if you could fold the paper so that the two distant points touch each other? What if you could poke a hole through both layers and create a tunnel connecting them? Suddenly, the shortest path isn't across the surface of the paper anymore. It's through the tunnel, through a higher dimensional space that bypasses the normal geometry of the surface entirely. This is exactly what a wormhole does with space-time. Instead of traveling the long way around through normal three-dimensional space, you take a shortcut through higher dimensional space that connects distant regions directly. The entrance to the wormhole might be here on Earth, while the exit opens up near a star system thousands of light years away. Step through the entrance, and you emerge at your destination almost instantaneously, having bypassed the normal speed limit not by going faster than light, but by taking a route that's fundamentally shorter. The mathematics of wormholes are surprisingly straightforward, at least in principle. Einstein's field equations describe how matter and energy curve space-time. Under the right conditions, that curvature can become so extreme that space-time essentially folds back on itself, creating a bridge between distant regions. The simplest type of wormhole is called a Schwarzschild wormhole, named after Karl Schwarzschild, who found one of the first exact solutions to Einstein's equations. These wormholes connect two black holes in different parts of the universe. Fall into one black hole, and theoretically, you could emerge from the other, having traveled an enormous distance through the connecting tunnel. But there's a catch, and it's a big one. Schwarzschild wormholes are completely unstable and non-traversable. The tunnel connecting the two black holes exists for only an infinitesimally short time before collapsing. Even a single photon trying to travel through the wormhole would cause it to collapse before the photon could complete the journey. And even if you could somehow traverse it, you'd be torn apart by the extreme tidal forces near the black hole horizons. This led physicists to ask a more refined question. Could there be stable, traversable wormholes that would allow matter and energy to pass through safely? The answer, discovered through decades of research, is a qualified yes. But like the Alcubierre drive, traversable wormholes require something that might not exist in nature. To keep a wormhole open and stable, you need what physicists call exotic matter. This isn't just any unusual form of matter. It's matter with properties that seem to violate some of our most basic assumptions about how the universe works. Specifically, you need matter that violates the null energy condition, a fundamental principle that states that energy density should never be negative along the path of a light ray. Think of it this way. Gravity is attractive. Mass and energy curve spacetime in a way that pulls things together. This is why planets orbit stars, why galaxies hold together, why the universe tries to collapse under its own weight. To keep a wormhole throat open against the natural tendency of spacetime to collapse, you need something that pushes spacetime apart. You need anti-gravity, and that requires exotic matter with negative energy density. The amounts of exotic matter required are staggering. To create a wormhole large enough for a spacecraft to pass through, you'd need exotic matter with negative mass equivalent to several times the mass of our Sun, all concentrated in a thin shell around the wormhole throat. We're talking about manipulating more matter than exists in our entire solar system, and it needs to be a form of matter that we've never observed in nature. But exotic matter isn't just science fiction. We know it exists, at least in microscopic quantities. The Casimir effect, which creates negative energy density between closely spaced metal plates, proves that exotic matter is real. Quantum field theory predicts that virtual particles in the vacuum can create regions of negative energy under certain conditions. The challenge is scaling these tiny quantum effects up to macroscopic levels. Some physicists have proposed ingenious ways to amplify quantum effects to create macroscopic amounts of exotic matter. What if you could use powerful electromagnetic fields to squeeze the quantum vacuum? What if you could use rotating superconductors to twist space-time and extract energy from the vacuum itself? What if you could find naturally occurring regions of exotic matter in the universe? These are all highly speculative ideas, but they suggest that exotic matter production might not be forever impossible. We might just need to discover the right techniques for manipulating quantum fields on large scales. Even if we could produce the necessary exotic matter, building a traversable wormhole would present unprecedented engineering challenges. The wormhole would need to be precisely constructed with exotic matter distributed in exactly the right configuration. Too little exotic matter, and the wormhole collapses. Too much, and it becomes unstable in other ways. The wormhole would also need to be anchored somehow. Natural wormholes, if they exist, would likely be microscopic and would move around unpredictably as space-time fluctuates. To be useful for transportation, a wormhole would need to be held in a fixed location, possibly using massive objects as anchors on both ends. But here's where wormholes become even more exotic. If you can build one traversable wormhole, you can potentially build a time machine. This isn't science fiction speculation. It's a direct consequence of general relativity. Here's how it works. Suppose you create a wormhole connecting Earth to a point near Alpha Centauri, 4 light-years away. Initially, clocks at both ends of the wormhole show the same time. But now you take one end of the wormhole and accelerate it to very high speed, then bring it back to Earth. Because of time dilation, the accelerated end ages more slowly than the stationary end. When you bring the accelerated end back to Earth, you now have a wormhole connecting 2 different times, as well as 2 different places. Step through one end, and you emerge from the other end at an earlier time. You've created a closed time-like curve, a path through space-time that loops back on itself. This possibility creates what physicists call the grandfather paradox. If you can travel back in time, you could potentially prevent your own grandfather from meeting your grandmother, preventing your own birth, and creating a logical contradiction. How can you prevent your own birth if you were never born to travel back in time in the first place? Some physicists argue that this paradox proves traversable wormholes can't exist. Others suggest that quantum mechanics or unknown physics might prevent paradoxes from forming. Stephen Hawking proposed his chronology protection conjecture, which states that the laws of physics somehow prevent the formation of closed time-like curves that could lead to paradoxes. But the mathematics of general relativity allows wormhole time machines, whether they lead to paradoxes or not. This suggests either that our understanding of physics is incomplete, or that the universe has subtle mechanisms that prevent paradoxes while still allowing exotic space-time geometries. Recent research has explored even more exotic possibilities. What about wormholes that connect not just different places in our universe, but different universes entirely? What about wormholes that exist in higher dimensional space, invisible to us, but potentially detectable through their gravitational effects? What about microscopic wormholes that form naturally in the quantum foam of space-time at the smallest scales? Some theories suggest that black holes might naturally create wormholes connecting to other regions of space-time. When matter falls into a black hole, instead of being crushed to infinite density at the singularity, it might emerge from a white hole in another part of the universe. Black holes and white holes would be connected by Einstein-Rosen bridges, creating a natural wormhole network throughout the cosmos. If such natural wormholes exist, they might be detectable through their effects on light and matter. A wormhole mouth would act like a gravitational lens, bending light rays in characteristic ways. The distortion patterns might be distinguishable from those created by ordinary massive objects, giving us a way to search for wormholes using astronomical observations. NASA and other space agencies have actually looked for signatures of wormholes in astronomical data. So far, they haven't found any convincing evidence, but the search continues. If natural wormholes exist, finding them could revolutionize our understanding of the universe and possibly provide ready-made shortcuts across cosmic distances. Even if we never learn to build wormholes ourselves, discovering natural ones could transform human civilization. Imagine finding a wormhole mouth in our solar system that connects to a distant galaxy. Suddenly, that galaxy becomes as accessible as the moon. We could explore billions of star systems, potentially discovering countless forms of alien life, all without ever exceeding the speed of light. But we shouldn't wait for natural wormholes to be discovered. The physics allows artificial wormholes in principle, and the engineering challenges, while enormous, might not be insurmountable forever. We're already learning to manipulate quantum fields in increasingly sophisticated ways. We're beginning to understand the relationship between quantum mechanics and gravity. We're developing technologies that would have seemed like magic just a few decades ago. Wormholes represent the second major loophole in Einstein's speed limit. Like the Alcubierre drive, they respect the fundamental rule that nothing can move through local space faster than light. Instead, They bypass the rule entirely by creating shortcuts through higher dimensional space that make faster than light travel irrelevant. The challenges are immense. Exotic matter production, space-time engineering, paradox prevention, and technologies that dwarf anything in our current capabilities. But the physics allows it, and human ingenuity has a remarkable track record of turning impossible dreams into everyday reality. Step through a wormhole, and you could emerge on the other side of the galaxy in seconds, having traveled a distance that light would take 100,000 years to cross. You wouldn't have broken the speed of light. You'd have made the speed of light irrelevant by taking a shortcut that bypasses normal space entirely. The universe is far stranger and more accommodating than our everyday experience suggests. Hidden in the mathematics of space-time are tunnels that could connect any 2 points in the cosmos. Shortcuts that could make the vastness of space just another engineering challenge to overcome. At the smallest scales of reality, where atoms give way to subatomic particles and the familiar rules of physics begin to break down, something extraordinary happens. The rigid speed limit that governs the macroscopic world starts to bend in ways that seem to mock Einstein's prohibition against faster-than-light phenomena. Particles appear to tunnel through barriers instantaneously. Information seems to travel between entangled particles instantly across arbitrary distances. The quantum world appears to be riddled with faster-than-light effects. But appearances can be deceiving, and the quantum realm is the master of deception. Every apparent violation of the cosmic speed limit turns out, upon closer inspection, to respect Einstein's fundamental rule in subtle but crucial ways. Yet these quantum effects hint at possibilities that could, theoretically, be scaled up to macroscopic levels and potentially exploited for faster-than-light communication or travel. The first and most famous of these quantum loopholes is quantum tunneling. This phenomenon was discovered in the early days of quantum mechanics, when physicists realized that particles don't always behave like tiny billiard balls bouncing off obstacles. Instead, they behave like waves that can sometimes pass through barriers that should be completely impenetrable according to classical physics. Imagine throwing a tennis ball at a brick wall. In the classical world, the ball bounces back every single time. The wall is simply too tall and thick for the ball to pass through. But in the quantum world, particles have a small but non-zero probability of appearing on the other side of barriers, even when they don't have enough energy to go over or around them. This isn't just theoretical speculation. Quantum tunneling is observed in laboratories around the world every day. It's the principle behind the scanning tunneling microscope, which can image individual atoms by measuring the quantum tunneling of electrons between a sharp metal tip and a surface. It's also crucial for the operation of many electronic devices, including the flash memory in your smartphone. But here's where quantum tunneling becomes relevant to faster-than-light travel. When particles tunnel through barriers, they appear to do so instantaneously. There's no time delay between the particle approaching the barrier and appearing on the other side. This has led some physicists to suggest that quantum tunneling might allow information to be transmitted faster than light. In the 1990s, physicist Günther Nimtz conducted a series of experiments that seemed to demonstrate faster than light signal transmission using quantum tunneling effects. He sent microwave pulses through barriers made of materials that should have blocked them completely. Not only did some of the signal get through via quantum tunneling, but it appeared to arrive faster than it would have if it had traveled through empty space at the speed of light. The results were stunning and controversial. Nimtz measured tunneling velocities that were 4.7 times the speed of light. Other researchers replicated the experiments and found even higher velocities, with some measurements suggesting speeds up to 1.7 times 10 to the power of 9 times the speed of light. These experiments sparked intense debate in the physics community. Had the cosmic speed limit finally been broken? Could quantum tunneling be the key to faster-than-light communication and perhaps even travel? The answer, as it turned out, was both yes and no. Yes, something was traveling faster than light in these experiments. But no, it wasn't useful information, and therefore, it didn't violate the fundamental principles of relativity. The key insight came from understanding exactly what was traveling faster than light during quantum tunneling. It wasn't the particles themselves, and it wasn't any useful information that could be extracted from the signal. Instead, it was what physicists call the group velocity of the wave packet, a mathematical construct that describes how the peak of a wave moves through space. Think of it this way. Imagine you're watching waves on the ocean. Individual water molecules aren't moving forward with the waves. They're moving in circles, rising and falling as each wave passes. But the wave pattern itself, the peak and trough structure, moves forward at a specific speed. This is the group velocity. In quantum tunneling, the peak of the wave packet can indeed travel faster than light through the barrier. But this doesn't mean that energy, information, or anything physical is traveling faster than light. It's more like a shadow that can move faster than light across a distant surface when you rotate a flashlight quickly. The shadow can exceed light speed, but it's not carrying any information or energy. To extract useful information from a quantum tunneling signal, you need to look at what physicists call the signal velocity, which is the speed at which the leading edge of the signal propagates. This leading edge, which carries the first information about the signal, always travels at or below the speed of light, even in quantum tunneling experiments. This distinction becomes crucial when you consider using quantum tunneling for faster-than-light communication. You might be able to send a signal through a barrier faster than light could travel around the barrier, but you can't send information faster than light could travel directly between the sender and receiver. The apparent faster-than-light transmission is really just a shortcut through the barrier, not a true violation of causality. But quantum tunneling isn't the only quantum effect that seems to violate the speed limit. The second, and perhaps more famous example, is quantum entanglement, a phenomenon that Einstein himself called spooky action at a distance. Quantum entanglement occurs when two or more particles become correlated in such a way that the quantum state of each particle cannot be described independently. Instead, they form a single quantum system, even when separated by vast distances. Measuring the properties of one particle instantly determines the properties of its entangled partners, regardless of how far apart they are. This correlation appears to be instantaneous. When scientists measure the spin of an entangled electron in New York, the spin of its partner in Tokyo is determined immediately, faster than light could travel between the two cities. Experiments have confirmed this instantaneous correlation over distances of hundreds of kilometers, and there's no theoretical limit to how far apart entangled particles can be. The implications seem revolutionary. If measuring one particle instantly affects its entangled partner, couldn't we use this effect to send information faster than light? Couldn't we build a quantum communication system that would allow instant communication across any distance? Unfortunately, the answer is no, and the reason reveals another subtle but crucial aspect of the cosmic speed limit. While the correlations between entangled particles are indeed instantaneous, they don't allow you to transmit information faster than light. Here's why. When you measure an entangled particle, you get a random result. You might find that an electron is spinning up or spinning down, but there's no way to control which result you get. The measurement outcomes are fundamentally random, determined by the probabilistic nature of quantum mechanics. Your measurement does instantly determine the state of the entangled partner, but the person measuring the partner particle still sees random results. They can't tell whether you've made a measurement or not just by looking at their own results. To compare your measurements and see the correlations, you need to communicate through normal channels, which are limited by the speed of light. It's like having two coins that are magically linked so that when one shows heads, the other always shows tails. Flipping one coin instantly determines the result of the other, but the person with the second coin can't tell whether the first coin has been flipped just by looking at their own coin. They see heads or tails with equal probability either way. This limitation is enshrined in what physicists call the no communication theorem, which proves mathematically that quantum entanglement cannot be used to transmit information faster than light. The correlations are real and instantaneous, but they're useless for communication. But some physicists have proposed clever ways to potentially circumvent this limitation. What if you could use multiple entangled particles and statistical analysis to extract information from what seems like random noise? What if you could use quantum interference effects to amplify the signal and suppress the noise? These ideas have led to serious research into quantum communication protocols that might, in principle, allow faster than light information transmission. None of them have succeeded so far, and most physicists believe they're fundamentally impossible due to deep principles of quantum mechanics and relativity. However, quantum entanglement has proven useful for other types of communication that don't violate the speed limit. Quantum cryptography uses entangled particles to create unbreakable encryption keys. Quantum teleportation uses entanglement to transfer the quantum state of one particle to another, though this process still requires classical communication at light speed to complete. The third quantum effect that seems to challenge the speed limit is the quantum Zeno effect, discovered in the 1970s. This effect shows that frequent measurements of a quantum system can actually freeze its evolution, preventing it from changing state, even when it would normally do so very quickly. The quantum Zeno effect gets its name from the ancient Greek philosopher Zeno, who proposed paradoxes about motion that seemed to prove that movement was impossible. In quantum mechanics, frequent measurements can create a similar paradox, where a system that should be changing rapidly becomes frozen in place. Some physicists have speculated that the quantum Zeno effect might be exploited to create faster than light effects. If you could use measurements to freeze the propagation of information through space, you might be able to create situations where information appears to jump from one location to another without traveling through the intervening space. This is highly speculative, and no one has demonstrated how such an effect could work in practice. The quantum Zeno effect has been observed in laboratory experiments, but only on individual particles, and only for very short time periods. Scaling it up to macroscopic levels or using it for faster than light communication remains purely theoretical. There are other quantum effects that seem to hint at faster than light possibilities. Quantum field theory predicts that the vacuum of space is filled with virtual particles that pop into existence and disappear again on timescales shorter than the uncertainty principle allows us to observe directly. Some of these virtual particle interactions appear to occur faster than light, though they can never be used to transmit information. The Casimir effect, which we encountered in our discussion of wormholes and the Alcubierre drive, is one manifestation of these virtual particle interactions. Two metal plates in a vacuum attract each other because there are fewer virtual particles between the plates than in the surrounding vacuum. This creates a region of negative energy density, exactly the kind of exotic matter needed for warp drives and traversable wormholes. Some physicists have proposed that we might be able to amplify Casimir effects or similar quantum phenomena to create macroscopic amounts of exotic matter. If successful, this could provide the negative energy needed for Alcubierre drives or the exotic matter needed for traversable wormholes. But these ideas remain highly speculative. The quantum effects we can currently observe and control operate on microscopic scales with tiny amounts of energy. Scaling them up to macroscopic levels would require technologies that are far beyond our current capabilities, if they're possible at all. The quantum world also suggests other possibilities for circumventing the speed limit. Quantum mechanics allows for superposition, where particles can exist in multiple states simultaneously until they're measured. What if you could create a macroscopic object in a superposition of being in two different locations? Could such an object effectively teleport from one place to another without traveling through the intervening space? This idea faces enormous practical challenges. Quantum superposition is extremely fragile and is easily destroyed by interactions with the environment. Creating and maintaining a macroscopic superposition would require perfect isolation from all external influences, which is probably impossible for objects larger than individual molecules. But quantum mechanics is full of surprises, and new effects are still being discovered. In recent years, physicists have observed quantum entanglement in increasingly large systems, from molecules to tiny mechanical oscillators. They've demonstrated quantum teleportation over increasing distances, from meters to hundreds of kilometers. They've found new ways to manipulate quantum states and control quantum systems. Each advance brings us closer to understanding the fundamental limits of what's possible in the quantum world. While none of these advances have led to faster than light communication or travel, they've revealed that the quantum realm is far richer and more complex than we initially realized. The quantum effects we've discovered so far respect the cosmic speed limit in clever ways that preserve causality, while still allowing phenomena that seem to violate our everyday understanding of space and time. Particles tunnel through barriers instantaneously, but information doesn't travel faster than light. Entangled particles correlate instantly across any distance, but you can't use these correlations to send messages faster than light. These limitations might be fundamental, built into the deepest structure of quantum mechanics and relativity, or they might be technological challenges that could be overcome with sufficiently advanced understanding and control of quantum systems. The quantum world has already given us technologies that would have seemed impossible just decades ago. Quantum computers that can solve certain problems exponentially faster than classical computers. Quantum sensors that can measure tiny changes in gravitational fields or magnetic fields with unprecedented precision. Quantum communication systems that provide unbreakable security. Perhaps the quantum world holds even greater surprises in store. Perhaps there are quantum effects we haven't discovered yet that could provide new pathways to faster-than-light phenomena. Perhaps we'll learn to manipulate quantum fields in ways that allow us to create macroscopic wormholes or exotic matter or space-time distortions. Or perhaps the quantum world will continue to tease us with apparent faster-than-light effects that always turn out to respect the fundamental speed limit when examined closely. Either way, the quantum realm remains one of the most promising places to look for loopholes in Einstein's cosmic barrier. Recent advances in quantum technology have brought these speculative possibilities closer to experimental reality. Quantum computers are now routinely manipulating quantum states in ways that seemed impossible just decades ago. IBM's quantum computers can maintain quantum coherence across dozens of qubits for significant periods. Google's quantum computer achieved quantum supremacy by performing calculations that would take classical computers thousands of years. These advances in quantum control suggest that we might eventually be able to scale quantum effects up to macroscopic levels. If we can control the quantum states of billions or trillions of particles simultaneously, we might be able to create macroscopic quantum superpositions or large-scale quantum tunneling effects. Some physicists have proposed using quantum computers themselves as tools for exploring faster-than-light possibilities. What if you could use quantum algorithms to simulate the behavior of exotic matter or wormhole geometries? What if quantum error correction could be used to stabilize otherwise unstable, faster-than-light effects? These ideas are highly speculative, but they point toward a future where quantum technology might provide new pathways to faster-than-light phenomena. We're already seeing quantum effects scaled up to larger and larger systems. Quantum entanglement has been demonstrated in systems containing millions of atoms. Quantum superposition has been observed in objects visible to the naked eye. The boundary between the quantum world and the classical world is becoming increasingly blurred. As quantum technology advances, we might discover new ways to exploit quantum effects that seemed impossible when quantum mechanics was first developed. Another frontier in quantum, faster-than-light research involves the manipulation of vacuum energy. The quantum vacuum is not empty space, but a seething foam of virtual particles that pop into existence and disappear again on timescales shorter than the Heisenberg uncertainty principle allows us to observe directly. Some theories suggest that vacuum energy could be harvested and manipulated to create exotic effects. The Casimir effect demonstrates that vacuum energy is real and measurable. Researchers have proposed using arrays of Casimir plates to amplify these effects, potentially creating regions of negative energy density large enough to power warp drives or stabilize wormholes. Dynamic Casimir effects, where the boundaries of a cavity are moved rapidly, can actually create real particles from the quantum vacuum. These effects have been observed in laboratory experiments using superconducting circuits. If they could be scaled up and controlled precisely, they might provide a pathway to exotic matter production. Zero-point energy extraction remains one of the most controversial topics in physics. Many researchers dismiss it as impossible, arguing that extracting energy from the vacuum would violate thermodynamics. But others point out that the universe itself extracted enormous amounts of energy from the vacuum during cosmic inflation, suggesting that vacuum energy extraction might be possible under the right conditions. The holographic principle, emerging from string theory and quantum gravity research, suggests that all the information in a volume of space can be encoded on its boundary. This implies that space itself might be emergent from more fundamental quantum information processing. If space is made of quantum information, then manipulating quantum information might allow us to manipulate space itself. This leads to radical possibilities for faster-than-light travel. If you could process quantum information faster than light, you might be able to effectively move through space faster than light by manipulating the quantum information that creates space. This wouldn't violate relativity because you wouldn't be moving through space. You'd be changing the nature of space itself. Quantum field theory in curved spacetime, the merger of quantum mechanics with general relativity, predicts effects that don't exist in either theory alone. Hawking radiation from black holes is one example. The Unruh effect, where accelerated observers see particles in what inertial observers consider empty space, is another. These effects suggest that the relationship between quantum mechanics and spacetime is far richer than we currently understand. There might be quantum spacetime effects that could be exploited for faster-than-light phenomena. Perhaps accelerated quantum systems could create spacetime distortions. Perhaps quantum field fluctuations could be amplified to macroscopic levels. The ADS-CFT correspondence, one of the most important discoveries in theoretical physics over the past few decades, shows that quantum field theories in flat space can be equivalent to gravitational theories in curved spacetime with extra dimensions. This suggests deep connections between quantum information and gravity that we're only beginning to understand. If quantum information and gravity are fundamentally connected, then advances in quantum information processing might lead to new ways of manipulating gravity and spacetime. Quantum computers might eventually be powerful enough to simulate gravitational effects directly, providing new insights into how spacetime can be manipulated. Some researchers have proposed that consciousness itself might play a role in quantum mechanics and potentially in faster-than-light phenomena. The measurement problem in quantum mechanics. The question of why quantum superpositions collapse when observed remains unsolved. Some interpretations suggest that consciousness is fundamental to quantum mechanics. If consciousness can affect quantum systems, and if quantum systems can affect spacetime, then consciousness might be able to influence spacetime directly. This could potentially provide a biological pathway to faster-than-light phenomena, though such ideas remain highly speculative and controversial. Quantum biology, the study of quantum effects in living systems, has revealed that quantum mechanics plays important roles in photosynthesis, bird navigation, and possibly even consciousness itself. These discoveries suggest that biological systems have evolved sophisticated mechanisms for exploiting quantum effects. Perhaps advanced biological systems, or hybrid biological quantum systems, could exploit quantum effects in ways that allow faster-than-light phenomena. Evolution has produced solutions to seemingly impossible problems before. It's conceivable that evolution could find pathways to faster-than-light capabilities that human technology hasn't discovered yet. The many-worlds interpretation of quantum mechanics suggests that every quantum measurement creates parallel universes where all possible outcomes occur. If the many-worlds interpretation is correct, then there might be ways to access information from parallel universes or even to travel between them. This could provide a form of faster-than-light travel that bypasses normal space entirely. Instead of moving through space faster than light, you could move between parallel versions of space where you're already at your destination. This would require understanding and controlling the branching of quantum realities, which is far beyond current capabilities but might be possible in principle. Quantum error correction, developed for quantum computing, shows that quantum information can be protected against decoherence and noise by encoding it in multiple quantum systems simultaneously. This suggests that quantum effects might be more robust and scalable than previously thought. If quantum error correction can protect quantum information in quantum computers, perhaps similar techniques could protect exotic quantum states needed for faster-than-light phenomena. Maybe the instability that plagues theoretical, faster-than-light devices could be overcome using quantum error correction techniques. The field of quantum metrology uses quantum effects to make measurements with precision beyond what's possible with classical systems. Quantum sensors can detect gravitational waves, measure magnetic fields with unprecedented sensitivity, and track time with extraordinary accuracy. These advances in quantum sensing might eventually be sensitive enough to detect the tiny space-time distortions that faster-than-light devices would create. Better detection capabilities could accelerate research into faster-than-light phenomena by making it possible to observe effects that are currently too small to measure. Topological quantum states discovered in condensed matter physics are quantum states that are protected against certain types of disturbance by their topology rather than by energy gaps. These states can maintain their quantum properties even in the presence of noise and imperfections. Topological protection might be crucial for creating stable, faster-than-light effects. If exotic quantum states needed for faster-than-light phenomena could be protected topologically, they might remain stable enough to be useful for practical applications. The speed of light still stands as the ultimate limit for useful information transmission and energy propagation. But at the quantum level, the universe reveals hints of deeper possibilities, tantalizing clues that faster-than-light phenomena might be achievable if we can learn to harness the strange rules that govern reality at its most fundamental level. While physicists debate exotic matter and quantum loopholes, nature has been demonstrating faster-than-light phenomena on the grandest scales imaginable for nearly 14 billion years. The universe itself regularly and casually violates what most people think of as the cosmic speed limit, not by breaking Einstein's rules, but by exploiting the same loophole that makes Alcubierre drives theoretically possible. Space itself can move, expand, and deform at any speed whatsoever, and the universe takes full advantage of this fact. Right now, as you read these words, galaxies at the edge of the observable universe are racing away from us at more than 3 times the speed of light. Not through space, but with space, carried along by the expansion of the universe, like boats on a river that's flowing faster than the boats could ever travel on their own. This isn't speculation or theoretical physics. It's directly observable fact, confirmed by decades of astronomical measurements. The universe is expanding, and at sufficient distances, that expansion carries galaxies away from us faster than light could travel between them through normal space. To understand how this works, we need to go back to the beginning, not the beginning of human civilization or the formation of our planet or even our solar system, but the beginning of everything. The Big Bang, the moment when space and time themselves came into existence 13.8 billion years ago. But here's what most people misunderstand about the Big Bang. It wasn't an explosion in space, it was an explosion of space. The Big Bang didn't happen at a particular location and then spread outward into pre-existing empty space. Instead, it was the moment when space itself began expanding everywhere simultaneously. Imagine a balloon being inflated. As you blow air into the balloon, every point on the surface moves away from every other point. There's no center to the expansion, no special location where the expansion is happening faster or slower. Every point sees every other point moving away from it, and the farther apart two points are, the faster they separate. This is exactly what happens with the expansion of the universe, except instead of a two-dimensional balloon surface, we're dealing with three-dimensional space that's expanding into higher dimensions we can't directly perceive. The expansion was first discovered by Edwin Hubble in 1929, when he noticed that distant galaxies appeared to be moving away from us. More remarkably, the farther away a galaxy was, the faster it seemed to be receding. This relationship, now known as Hubble's law, provided the first evidence that the universe was expanding uniformly in all directions. Hubble measured the expansion by looking at the light from distant galaxies. As space expands, it stretches the wavelengths of light traveling through it. Light that was emitted as blue light from a distant galaxy arrives at Earth as red light, shifted toward longer wavelengths by the expansion of space during its journey. The amount of this redshift tells us how fast the galaxy is receding and how far away it is. The mathematics of cosmic expansion are surprisingly straightforward. The expansion rate is described by the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light years, the recession velocity increases by 70 kilometers per second. Let's follow this relationship to its logical conclusion. At a distance of 1 megaparsec, galaxies recede at 70 kilometers per second. At 10 megaparsecs, they recede at 700 kilometers per second. At 1,000 megaparsecs, they recede at 70,000 kilometers per second, which is about 23% of the speed of light. Keep going, and you reach what cosmologists call the Hubble distance, about 14 billion light-years away. At this distance, galaxies are receding from us at exactly the speed of light, 299,792,458 meters per second. But the universe doesn't stop there. Beyond the Hubble distance, galaxies recede faster than light. At 20 billion light-years, they're moving away at about 1.5 times light speed. At 30 billion light-years, it's over twice light speed. At 40 billion light-years, nearly 3 times light speed. These aren't theoretical calculations. We can actually observe galaxies that are receding faster than light by looking at light they emitted in the past when they were closer to us and receding slower than light. The most distant galaxies we can see are currently receding from us at nearly 3 times the speed of light, even though the light we're seeing from them was emitted when they were much closer. This creates a fundamental limit to what we can observe in the universe. Light emitted today by galaxies beyond the Hubble distance will never reach us, because space is expanding faster than light can traverse it. These regions are forever beyond our cosmic horizon, invisible and unreachable, no matter how long we wait or how powerful our telescopes become. But cosmic expansion at the current rate is nothing compared to what happened in the first moments after the Big Bang. During a period called cosmic inflation, space expanded exponentially, doubling in size every tiny fraction of a second. This expansion was so rapid that regions of space that were once close enough to exchange light signals were stretched apart faster than light could travel between them. The theory of cosmic inflation was proposed by Alan Guth in 1980 to explain several puzzling features of the universe. Why does the cosmic microwave background radiation, the afterglow of the Big Bang, have almost exactly the same temperature in all directions? Why is the universe so remarkably flat and uniform on the larger scales? Why don't we see exotic relics like magnetic monopoles that many theories predict should have been produced in the early universe? Inflation answers all these questions by proposing that the universe underwent a brief period of exponential expansion in its first fraction of a second. During inflation, space expanded by a factor of at least 10 to the power of 26, and possibly much more. Regions that were initially smaller than a proton ended up larger than a grapefruit in less than 10 to the power of minus 32 seconds. This expansion was driven not by matter or radiation, but by the energy density of space itself. According to inflation theory, empty space in the early universe had a positive energy density that caused it to expand exponentially. This is the same kind of effect that powers theoretical Alcubierre drives, except it happened naturally during the first moments of cosmic history. The expansion during inflation was so rapid that it dwarfs anything we've discussed so far. While current cosmic expansion carries distant galaxies away at a few times the speed of light, inflation carried regions of space apart at speeds that were trillions upon trillions upon trillions of times faster than light. To put this in perspective, imagine 2 points that were initially separated by the size of a proton, about 10 to the power of minus 15 meters. After inflation, these same 2 points would be separated by distances measured in light years, increases of over 10 to the power of 40 in size. If inflation lasted for 10 to the power of minus 35 seconds, the average expansion velocity would have been about 10 to the power of 50 times the speed of light. This isn't just theory. We can see the effects of inflation written across the sky in the cosmic microwave background radiation. Tiny quantum fluctuations that existed before inflation were stretched to cosmic scales by the exponential expansion. These fluctuations show up as tiny temperature variations in the cosmic microwave background, variations that eventually grew into the galaxies and galaxy clusters we see today. The cosmic microwave background provides a baby picture of the universe, showing us what it looked like when it was only 380,000 years old and had just become transparent to light. The patterns we see in this radiation match the predictions of inflation theory with extraordinary precision, providing strong evidence that cosmic inflation actually occurred. But inflation raises a profound question. If space could expand faster than light in the early universe, could it do so again? Could we somehow recreate the conditions that drove inflation and use them to propel spacecraft faster than light? This idea isn't as crazy as it might sound. Inflation was driven by what physicists call a scalar field, a type of energy field that permeates all of space. If we could learn to manipulate scalar fields, we might be able to create localized regions of exponential expansion that could carry spacecraft along with them. Such a propulsion system would work similarly to an Alcubierre drive, creating a bubble of expanding space that carries a spacecraft faster than light without requiring the spacecraft to move through its local space faster than light. The main difference would be that instead of using exotic matter with negative energy density, it would use scalar field energy similar to what drove cosmic inflation. The challenges would be enormous. We'd need to understand scalar fields well enough to control them precisely. We'd need to create the right energy densities to drive expansion without creating a runaway inflation that destroys everything around it. We'd need to figure out how to start and stop the expansion on command. But unlike exotic matter, scalar fields are known to exist. The Higgs field, discovered at the Large Hadron Collider in 2012, is a scalar field that gives mass to elementary particles. Dark energy, the mysterious force driving the current acceleration of cosmic expansion, might also be a scalar field. If we can learn to manipulate these fields, we might be able to harness the same forces that drive cosmic expansion. Some physicists have proposed that advanced civilizations might be able to create artificial inflation for faster-than-light travel, or even for universe creation. If you can create a region of space that undergoes eternal inflation, you've essentially created a new universe that branches off from our own, expanding forever and potentially developing its own galaxies, stars, and planets. This suggests that our own universe might be just one bubble in an infinite multiverse of inflating space, with new universes constantly being created through natural or artificial inflation events. Each universe would have its own physical laws and constants, determined by how the scalar fields that drive inflation eventually decay into ordinary matter and energy. The expanding universe also reveals another remarkable feature of faster-than-light phenomena. The galaxies that are receding from us faster than light aren't just moving away. They're carrying information with them that we can never access. Every galaxy beyond our cosmic horizon contains billions of stars, potentially trillions of planets, and possibly countless forms of life that we can never observe or communicate with. This creates what cosmologists call the ultimate cosmic loneliness. As the universe continues to expand and accelerate, fewer and fewer galaxies remain within our observable horizon. In the far future, billions of years from now, civilizations arising in our galaxy will see a universe that appears almost empty, with only our local group of galaxies visible against a dark sky. But cosmic expansion also suggests possibilities for faster-than-light communication that don't require exotic technology. If space itself is expanding faster than light at sufficient distances, then information encoded in the expansion itself might be able to travel faster than light through the universe. This is purely speculative, but some physicists have proposed that gravitational waves or other space-time disturbances might be able to propagate through expanding space in ways that effectively exceed the speed of light. If civilizations could learn to modulate the expansion of space itself, they might be able to send signals across cosmic distances faster than light could travel through normal space. The expanding universe demonstrates that faster-than-light phenomena are not just possible, but commonplace on cosmic scales. Space itself moves faster than light regularly and naturally, carrying matter and energy along with it, without violating any physical laws. The universe has been demonstrating faster than light travel for nearly 14 billion years, not by breaking Einstein's speed limit, but by exploiting the loophole that space itself can move at any speed. This cosmic example provides a proof of principle for faster than light travel through space-time manipulation. If space can naturally expand faster than light, then perhaps we can learn to create artificial expansions or contractions that allow controlled faster than light travel. The universe itself shows us that it's possible. We just need to figure out how to do it on command. The challenge isn't whether faster than light phenomena can exist. The universe proves they can. The challenge is learning to harness and control the same forces that drive cosmic expansion for our own purposes. If we can master the physics of space-time itself, the same physics that inflated the early universe and continues to expand space today, then the galaxy becomes accessible without ever violating the fundamental speed limit for motion through space. Nature has already broken the cosmic speed limit billions of times over. Now we just need to learn how to do it ourselves. After decades of theoretical breakthroughs and mathematical discoveries, after identifying multiple potential loopholes in Einstein's cosmic speed limit, the question remains: where do we actually stand today in the quest to achieve faster than light travel? What concrete steps are being taken to transform these exotic theoretical possibilities into engineering reality? The answer is both more promising and more sobering than most people realize. While we're still impossibly far from building a working faster-than-light drive, the scientific community has begun taking these concepts seriously enough to fund real research, conduct actual experiments, and develop the theoretical frameworks that might one day make the impossible possible. The most significant institutional effort began in 1996, when NASA established the Breakthrough Propulsion Physics Project, a formal research program dedicated to investigating revolutionary propulsion concepts that could enable interstellar travel within human lifetimes. For the first time in history, a major space agency was officially funding research into faster-than-light travel, anti-gravity, and other exotic propulsion concepts. The project was led by Mark Millis, a NASA engineer who recognized that conventional chemical rockets would never be sufficient for serious interstellar exploration. Even our most powerful rockets can barely achieve speeds of 50 kilometers per second, which would take over 25,000 years to reach the nearest star. Nuclear rockets might achieve a few percent of light speed, reducing the travel time to centuries, but this is still far too slow for practical interstellar missions. Millis and his team took a systematic approach to revolutionary propulsion research. Rather than dismissing faster-than-light travel as impossible, they asked what would be required to make it work. What forms of exotic matter or energy would be needed? What are the fundamental physical limits? What experiments could be conducted to test the underlying principles? The Breakthrough Propulsion Physics Project funded research into three main areas. First, they investigated propellantless propulsion, methods of generating thrust without ejecting mass, potentially allowing spacecraft to achieve much higher velocities than conventional rockets. Second, they studied faster-than-light travel concepts, including Alcubierre drives and traversable wormholes. Third, they explored breakthrough energy concepts that could provide the enormous power requirements for exotic propulsion systems. Over its 8-year lifespan, the project funded dozens of research proposals from universities and private companies around the world. Some investigated the Casimir effect and other quantum phenomena that might be scaled up to produce exotic matter. Others studied electromagnetic effects that might allow propellantless thrust generation. Still, others explored theoretical frameworks for faster-than-light travel and communication. One of the most intriguing research directions involved attempts to create and detect space-time distortions in laboratory settings. If Alcubierre drives work by warping space-time, then any functioning warp drive should produce measurable distortions that could be detected with sufficiently sensitive instruments. Harold White, working at NASA's Johnson Space Center, developed a theoretical framework for detecting warp drive signatures using laser interferometry. The basic idea is that a functioning warp drive would stretch and compress space in characteristic patterns that would show up as changes in the length of laser beams passing through the distorted region. White's team built an instrument called the White-Jude Warp Field Interferometer, designed to detect space-time distortions on the scale of a few parts in 10 to the power of 10. While this is incredibly sensitive by normal standards, it's still many orders of magnitude less sensitive than would be needed to detect the tiny space-time distortions that current technology might be able to produce. The interferometer experiments haven't detected any warp field effects yet, but they've established important upper limits on how strong any such effects could be. More importantly, they've demonstrated that space-time distortion detection is possible in principle, providing a pathway for testing more advanced warp drive concepts as they're developed. White also conducted theoretical work to refine Alcubierre's original drive design. He showed that by oscillating the warp field rather than keeping it constant, and by optimizing the geometry of the space-time distortion, the energy requirements for a functional warp drive could potentially be reduced from the mass energy of Jupiter to something closer to the mass of the Voyager spacecraft. This is still an enormous amount of energy, equivalent to converting about 700 kilograms of matter directly into energy via Einstein's E equals mc squared equation, but it represents a reduction in energy requirements of over 10 orders of magnitude, bringing warp drives from completely impossible to merely incredibly difficult. Other researchers have explored different approaches to exotic matter production. The Casimir effect demonstrates that negative energy densities can exist, but only in microscopic quantities between closely spaced conducting plates. Scaling this up to the amounts needed for warp drives would require revolutionary advances in quantum field manipulation. Some proposals involve using powerful electromagnetic fields to squeeze the quantum vacuum and amplify Casimir effects. Others suggest using superconducting circuits or rotating superconductors to extract energy from quantum fluctuations. Still, others explore whether certain materials or geometries might naturally produce regions of negative energy density. All of these approaches face the same fundamental challenge. The amounts of exotic matter needed for faster-than-light propulsion are enormous compared to anything we can currently produce. We can create negative energy densities that are billionths of the required strength. Bridging this gap would require not just technological advances, but fundamental breakthroughs in our understanding of quantum field theory and space-time physics. Research into traversable wormholes faces similar challenges. While the mathematics of wormhole physics are well established, creating a stable wormhole would require even more exotic matter than an Alcubierre drive. The exotic matter would need to be arranged in complex three-dimensional configurations with precise density distributions, far beyond anything we can currently achieve. Some researchers have explored whether natural wormholes might exist in the universe. If black holes naturally create Einstein-Rosen bridges to other regions of space-time, then we might be able to find and use existing wormholes rather than trying to create new ones. However, searches for wormhole signatures in astronomical data haven't found any convincing evidence for natural wormholes. The European Space Agency has also begun funding research into breakthrough propulsion concepts through their Advanced Concepts team. Like NASA's Breakthrough Propulsion Physics project, this program takes a systematic approach to revolutionary spaceflight technologies, funding both theoretical research and experimental investigations. One area of particular interest is electromagnetic propulsion systems that might not require exotic matter. The EM drive, proposed by British engineer Roger Scheuer, claims to generate thrust by bouncing microwaves around inside a tapered cavity. If it works, it would violate conservation of momentum, one of the most fundamental principles in physics. Multiple research groups have tested EM drive prototypes, with some claiming to measure tiny amounts of thrust. However, other researchers have failed to replicate these results, and most physicists remain skeptical that the EM drive actually works. The measured thrusts are so small that they could easily be explained by experimental errors or thermal effects rather than genuine momentum violation. Similar controversy surrounds other claimed breakthrough propulsion technologies. The Biefeld-Brown effect claims to generate thrust using high-voltage electrical fields, but repeated tests have shown that the observed effects are due to ion wind rather than genuine field propulsion. Cold fusion claims to produce nuclear energy without the extreme temperatures normally required, but these claims haven't been reliably reproduced. The challenge with breakthrough propulsion research is that extraordinary claims require extraordinary evidence, and the evidence for revolutionary new physics is often ambiguous or difficult to reproduce. This has led to a natural skepticism within the scientific community about claims of breakthrough technologies. However, this skepticism is balanced by recognition that revolutionary advances in physics have happened before and will likely happen again. Quantum mechanics seemed impossible to the physicists of the 19th century. Nuclear energy was dismissed as impractical just years before the first nuclear reactors were built. Laser technology was once called a solution looking for a problem. The current state of faster-than-light research can be summarized as follows. The theoretical foundations are solid. General relativity allows faster-than-light travel through space-time manipulation, and we understand the basic principles involved. The engineering challenges are enormous, but not necessarily impossible. We know what kinds of exotic matter and energy would be required, even if we can't produce them yet. What's missing is the crucial bridge between theory and engineering. We need breakthrough discoveries in exotic matter production, quantum field manipulation, or space-time physics that could make faster-than-light propulsion technologically feasible rather than just theoretically possible. Some of the most promising research directions involve quantum technologies that are advancing rapidly for other reasons. Quantum computers are learning to manipulate quantum fields in increasingly sophisticated ways. Metamaterials research is discovering materials with exotic electromagnetic properties that don't exist in nature. High-energy physics experiments are probing deeper into the fundamental structure of space-time. Any of these research areas could potentially yield discoveries that revolutionize our ability to manipulate space-time or produce exotic matter. The key insight from decades of breakthrough propulsion research is that faster-than-light travel isn't forbidden by physics. It's just incredibly difficult to achieve with current technology. Private companies and research organizations have also begun investigating breakthrough propulsion concepts. The Tau Zero Foundation, founded by former NASA researcher Mark Millis, continues to coordinate research into revolutionary spaceflight technologies. The Institute for Interstellar Studies explores both conventional and exotic approaches to interstellar travel. Some researchers are taking a different approach entirely, focusing on near-term technologies that could enable fast interstellar travel without requiring exotic physics. Fusion rockets could potentially achieve 10 to 20% of light speed, making interstellar missions possible within human lifetimes, even without faster-than-light travel. Antimatter rockets could go even faster, approaching significant fractions of light speed. These conventional approaches to fast space travel face their own enormous challenges. Fusion rocket technology is still in its infancy, with no working fusion rockets yet demonstrated. Antimatter production requires vast amounts of energy and can only produce microscopic quantities with current technology. Interstellar missions would require solving unprecedented problems in spacecraft design, navigation, and life support. But unlike faster-than-light propulsion, these conventional approaches don't require revolutionary new physics. They're engineering challenges rather than fundamental physics challenges. This makes them more likely to be achieved in the foreseeable future, even if they don't offer the dramatic capabilities of true faster-than-light travel. The search for faster-than-light travel has also driven advances in fundamental physics research. Studies of the Casimir effect have deepened our understanding of quantum field theory. Research into exotic matter has revealed new aspects of general relativity. Investigations of space-time manipulation have led to insights into the nature of gravity and the structure of the universe. These advances have practical applications beyond breakthrough propulsion. Precision measurements of space-time distortions could lead to new types of gravitational wave detectors. Better understanding of quantum field effects could improve quantum computing and quantum sensing technologies. Research into exotic materials could yield new technologies for energy storage, electromagnetic shielding, or other applications. The current state of faster-than-light research can be characterized as scientifically rigorous, but technologically premature. We understand the physics well enough to know that faster-than-light travel is possible in principle. We've identified the main technical challenges and begun developing the theoretical frameworks needed to address them. But we're still many decades, and possibly centuries, away from having the technology to build working faster-than-light propulsion systems. This doesn't mean the research is pointless, or that faster-than-light travel will never be achieved. History shows that seemingly impossible technologies often become routine given enough time and effort. The key is maintaining rigorous scientific standards while remaining open to revolutionary possibilities. The speed of light remains humanity's greatest barrier to exploring the cosmos. But for the first time in history, we have scientifically credible pathways for overcoming that barrier. The engineering challenges are staggering, but they're not necessarily insurmountable. The universe itself has shown us that faster-than-light phenomena are possible. Now we just need to learn how to harness them ourselves. Here we stand at the edge of the impossible, staring across the vast gulf between our current capabilities and our cosmic ambitions. The speed of light, 299,792,458 meters per second, still stands as the ultimate barrier between humanity and the stars. But for the first time in our species' history, that barrier no longer looks impenetrable. We've seen how Einstein's prohibition against faster-than-light travel isn't quite what most people think it is. The cosmic speed limit applies specifically to local motion through space, not to space itself. This distinction opens up a universe of possibilities that seemed impossible just decades ago. Space can expand, contract, twist, and deform at any rate whatsoever. And if we can learn to surf those waves in space-time, we can cross galactic distances without ever violating the fundamental speed limit. The Alcubierre drive shows us one path forward. By contracting space ahead of a spacecraft and expanding it behind, we could create a warp bubble that carries us faster than light while keeping us stationary relative to our local space-time. The engineering challenges are staggering, requiring exotic matter with negative energy density equivalent to the mass of planets or stars. But Harold White's refinements have reduced these requirements by many orders of magnitude, bringing warp drives from completely impossible to merely incredibly difficult. Traversable wormholes offer another route to the stars. These shortcuts through higher dimensional space could connect distant regions of the universe, making travel times irrelevant rather than just faster. The exotic matter requirements are even more demanding than for warp drives, and the stability challenges are immense. But the mathematics work, the physics allow it, and the universe itself might contain natural wormholes waiting to be discovered. The quantum world hints at deeper possibilities. Quantum tunneling appears to allow instantaneous transmission through barriers, though closer examination reveals that no useful information travels faster than light. Quantum entanglement creates instant correlations across arbitrary distances, but these correlations can't be used for faster-than-light communication. These effects respect Einstein's speed limit in subtle ways that preserve causality while still demonstrating that reality is far stranger than our everyday experience suggests. Perhaps most remarkably, the universe itself regularly demonstrates faster-than-light phenomena on the grandest scales imaginable. Cosmic expansion carries distant galaxies away from us at several times the speed of light. During cosmic inflation, space expanded exponentially, stretching regions apart at speeds that were trillions upon trillions of times faster than light. These natural examples prove that faster-than-light motion is not just theoretically possible, but commonplace in our universe. The scientific foundations for faster-than-light travel are solid. General relativity explicitly allows space-time manipulation that could enable warp drives and wormholes. Quantum mechanics reveals effects that seem to transcend normal speed limits, even if they can't yet be harnessed for practical faster-than-light applications. Cosmology shows us that space itself follows no speed restrictions and regularly expands faster than light on cosmic scales. What's missing is the technology to bridge the gap between theoretical possibility and engineering reality. We need to learn how to produce and control exotic matter with negative energy density. We need to understand how to manipulate quantum fields on macroscopic scales. We need to figure out how to create stable space-time distortions that can be controlled and directed. These aren't just engineering challenges. They're fundamental physics challenges that will require revolutionary advances in our understanding of quantum gravity, the nature of space-time, and the relationship between matter and geometry. We're not talking about building better rockets or more efficient engines. We're talking about learning to manipulate the fundamental structure of reality itself. But history suggests that such revolutionary advances are possible. Newton's laws of motion seemed to describe reality completely until Einstein showed that space and time are relative and interconnected. Classical physics appeared complete until quantum mechanics revealed that reality is fundamentally probabilistic and observer-dependent. Our current understanding of physics, impressive as it is, will certainly be superseded by deeper theories that reveal new possibilities. The next breakthrough might come from quantum gravity research, where physicists are trying to unify general relativity with quantum mechanics. String theory, loop quantum gravity, and other approaches to quantum gravity all predict effects that don't exist in our current theories. Some of these effects might provide new pathways to exotic matter production or space-time manipulation. The breakthrough might come from cosmology, where dark energy and dark matter hint at physics beyond our current understanding. If dark energy is a scalar field similar to what drove cosmic inflation, learning to manipulate such fields could provide the key to faster-than-light propulsion. If dark matter interacts with space-time in ways we don't yet understand, it might offer new approaches to space-time engineering. The breakthrough might come from quantum technology, where we're learning to manipulate quantum systems with unprecedented precision. Quantum computers, quantum sensors, and quantum communication systems are pushing the boundaries of what's possible with quantum field manipulation. These advances might eventually be scaled up to macroscopic levels that could enable exotic matter production. Or the breakthrough might come from completely unexpected directions. The history of physics is full of discoveries that revolutionized our understanding in ways that couldn't have been predicted. Radioactivity, quantum mechanics, relativity, and countless other discoveries opened up possibilities that were literally unimaginable before they were made. What we can say with confidence is that faster-than-light travel is not forbidden by the laws of physics as we currently understand them. The universe allows it in principle. Whether we'll ever develop the technology to achieve it is another question, but the fundamental barriers are technological rather than physical. The implications of achieving faster-than-light travel would be transformative beyond imagination. The Milky Way galaxy, with its 400 billion stars and potentially trillions of planets, would become accessible within human lifetimes. Other galaxies, currently separated from us by millions or billions of years at light speed, could be reached in reasonable timeframes. We could explore countless worlds, potentially discovering forms of life that evolved under completely different conditions. We could spread human civilization across the galaxy, ensuring our long-term survival even if catastrophes befell our home planet. We could access resources and energy sources on scales that dwarf anything available in our solar system. But even if faster-than-light travel proves forever impossible, the research itself is driving advances that benefit humanity in countless ways. Studies of exotic matter are deepening our understanding of quantum field theory. Research into space-time manipulation is revealing new aspects of gravity and cosmology. Attempts to detect warp signatures are pushing the limits of precision measurement technology. These advances have practical applications in quantum computing, gravitational wave detection, precision navigation, fundamental physics research, and countless other fields. The quest for faster-than-light travel is advancing human knowledge and capability, even if it never achieves its ultimate goal. The cosmic speed limit may be the ultimate test of human ingenuity and determination. For nearly a century, the speed of light has seemed like an insurmountable barrier to our cosmic ambitions. But as we've seen, that barrier isn't quite what it appears to be. There are loopholes, pathways around the prohibition that could make the impossible possible. Whether we'll find those pathways and learn to exploit them remains to be seen. The challenges are enormous, possibly greater than any we've ever faced as a species, but the potential rewards are equally enormous. The entire universe could become our backyard if we can learn to manipulate the fundamental forces that govern space-time itself. The speed of light, 299,792,458 meters per second, still stands as the fastest thing in the universe and the hardest barrier to break. But if we can reshape space itself, if we can surf the waves in space-time, rather than swimming against them, the path beyond may be possible. The cosmos is vast beyond human comprehension, filled with wonders we can barely imagine. Faster than light travel would make that vastness accessible, transforming humanity from a single planet species into a truly cosmic civilization. The universe has shown us that it's possible. The question is whether we're clever enough, determined enough, and patient enough to figure out how to do it ourselves. The journey to the stars may be the greatest adventure in human history, and it might just be possible after all.